Hello everyone. Welcome to the seventh. First of all, I would like to thank you all for joining the seventh edition of the EIT Raw Material Sign Magellan Roundtable series. As many of you have joined before, this is a joint effort led by SIGN, the Strategic Impact Group network of the EIT raw materials on rare earths and magnets, and the Magellan project, which is coordinated by the leading industry player, Orano. So before we start the webinar formally, a couple of words on what is the Strategic Impact Group network. The SIGN, we call it in short, is a new initiative of the EIT raw materials on specific raw materials value chain. The first two signs on rare earths and magnet and battery materials were launched in last April in a dedicated expert forum in Frankfurt. And there will be a couple of more, signs coming in coming months. And the basic idea of especially the sign on rare earths and magnet is that to formulate a coordinated approach and set of actions to address challenges and related to de-risking the EU rare earths and magnet supply chain and enhance industry resilience. So we're building a network of the partners across the rare earth and magnet value chain. And Magellan like I said, is a EU Horizon project, which aims to develop and demonstrate in an operational environment a novel and disruptive, cost-competitive, environmentally friendly solution leveraging functional recycling and highly advanced process for manufacturing permanent magnets and new optimized designs for electric vehicle traction motors. We are quite advanced in this project, as you may have seen in news that last month, Orano and CEA were the leaders in the project, were launched a pilot line for the rare earths magnet recycling and the magnet manufacturing. And so again, I have great pleasure to welcome you all for this webinar. And you would be able to, raise your questions in the chat box. There is a Q&A tab. So please actively engage with the speakers. Please, leave your questions there, and we would be happy to, raise these questions for you to the speakers. So we have very, very distinguished speakers this time, as the topic itself is the permanent magnet applications in the automotive sector and the circular economy challenges. So we have three speakers from, for example, from the reputed company on the automotive sector, ZF, and we have from VDA, the German automotive agency, and we have from IFPEN. So the first speaker is David Schuller from ZF, and I would like to welcome him. He has been working for ZF for last 7 years in the position of a material expert for material selection of traction drives, where, as you know, the permanent magnet and rare earth play an important role. And he was responsible for strategic material decision and bundle all sustainability topics related to materials for traction drives in a chief engineering position. He is, of course, he obtained a doctoral degree from KIT Karlsruhe and Erlangen University in Germany on soft magnet material composite for high frequency applications. So I welcome now David Schuller. David, floor is yours. Please start the presentation.
Thank you very much, Nabil. Do you see already my slides?
Yes.
Okay, fantastic. Yeah, Zoom is not my most common tool. So thank you very much for the chance to be part of this webinar and to give you some insights on the topic traction drives and the usage of rare earth magnets. I will jump to the first slide. So at first, I want to answer the question, who is ZF Friedrichshafen currently in the field of traction drives? Here I want to show you some historical schematic curve. So we started really early, so 1989 with first eDrive developments. And then it was a logical step that ZF, as a famous producer of transmissions, add a eDrive and say, now we have a hybrid system in the portfolio. And so we started a few generations of hybrids, and we are proud that since 2022, we have currently the fourth generation of our hybrid systems already in production, available on the market. But we have not only hybrids, we started 2020 with first ASM applications, so with aluminum cage, and in 2021 with first pure e-axles. And this curve is really also a good schematic idea of our growing. So the first projects 10 years ago were really small, but the last years we see some ramp up, some larger interest in electromobility. And so we had really something like exponential growth and a lot of new projects. And so we produced now more than 5 million machines, and can say, yeah, we have some understanding of eDrives and have some expertise in this field. And something I want also add is ZF, Zahnradfabrik, was in the past a company really famous for gearboxes, for mechanical components, and that changed the last decades. So we are currently more like a technology company that offers software, power electronics, sensors, autonomous driving, shuttles, braking systems, steering systems. So it's more like a really a system supplier. Yeah, and focusing only on eDrives, you can here see some examples. So we have, like already mentioned, ASM machines, PSM, also SCSM. So we use copper windings instead of magnets inside of the rotor. We have a variety of different hybrid systems. Range extender, we have own patents and developments in the field of hairpin innovations to really produce more compact designs, develop own power electronics with collaboration partners, use our old expertise in the field of mechanical components. And we are currently one of a handful system suppliers that really can offer you a full spectrum of eDrive software, power electronics, suspension, steering system, braking system. So you need only the battery and then you can drive. All the examples were more related to passenger cars. So here see you some pictures, some illustrations of typical products. But we have also a lot of activities in the field of commercial cars. Because of acquisition in 2020, ZF is currently the largest supplier of commercial cars applications. So we have also eDrives for bus applications, trucks, and so on. And so we are currently in a situation we can electrify more or less everything. If we see the development targets the last years, there was really a new challenge to be faster, because of the fact that we have more competition in the field of eDrives, that the development times have to be reduced also because of the Chinese speed. One topic was really to be more cost effective, more to show higher agility, to be faster in the development. And here for example, or we offer since a few years now a base kit application. So it's a modular system, eDrive toolbox, where we have often same components and only changing, for example, the active length. With such a base kit, we are really fast in the market, faster also in our development times because it's already ready and can only be tailored. The second one, like always, we have to be more efficient also in our eDrive designs. We have to be innovative with new technologies like better cooling or high voltage applications. That was one really strong pillar and was something that was really fantastic also for me, because it's more like a passion, that sustainability was important. So the last years, 2 years, I would say, there were new questions that were related to the point, where do you buy your rare earths, on which mining operation, what is a separation process? And so we had really also the challenge to go more inside of the production of the magnets. So not only buy magnets, we understand, or we try to understand the full supply chain behind our magnet suppliers. And another thing that was also producing some rumors, I would say, in ZF side, is also the point, is a magnet really sustainable? So can we buy in China magnets that may be coming with rare earths from Myanmar? can we really build up a traceability or a robust supply chain to be sure that our magnet is sustainable, or have we to jump to other alternatives? And that was also the reason why we developed SCSM, so the already mentioned design where you have copper windings in the rotor instead of magnets. So really go the way not using magnets anymore. Yeah, I want to focus in the presentation on the red line green magnets, and want to show you now some levers that we have to reduce the product carbon footprint, the PCF of a magnet, to reduce the CO2 footprint of a magnet. If we speak about CO2 footprint, one easy way is you take your eDrive and list the materials, the raw materials, and collect a rough idea how large is the CO2 footprint of a magnet compared with other material classes. And that is shown here. So copper, for example, in a standard eDrive will have an impact of about 7%. Then you have e-steel produced by blast furnaces, the most common way. Also have a lot of waste because of the punching process, has a really high impact on the CO2 footprint. Then aluminum, and the last one, magnets, roughly 37% contribution to the CO2 footprint of an e-machine. And so one question, how can we reduce such a high value? How can we buy more sustainable magnets? And here I want to give you some insights in 3 different routes, I would say. So the first one is to get an insight in the strategic supply base. So where can we buy green magnets? Second one is how do we select magnets? So how can we be sure that we really choosing the best solution for a certain application? And the last one, what can we do from a more innovative or from a technological side to reduce the requirement on the magnets, and with this also the composition, and can open the door for more sustainable magnets. Starting with the first one, you have to know if you requesting magnets globally, you will find roughly 100 different magnet suppliers. And more or less all of them will explain you that they have the GBD process invented, that they have very sustainable processes. So it's really hard to get at first a rough idea in all this variety that you see on the market. It's a really a market with a lot of competition and a lot of players with all different USPs that you really can attack. And in the past, it was not the important thing to say if we buy the best magnet, is it also a green magnet? No, because normally we buy a magnet because of performance or because of price, or sustainability was always, from the prioritization point of view, a secondary topic. If we see our situation as ZF, we have production locations on all 3 larger regions. Yeah, and the normal way was we have to buy cheap magnets with high performance. And so the most magnets come from Asia, and especially from China, because in China we have really a situation, we have very cheap magnets, because of the fact that they are number 1 in resources, number 1 in mining capacity, separation, and magnet supply production. They have a large variety of suppliers available. Yeah, and they have also currently the largest market for EV, and that results in the fact that they are more innovative, that they are really, from a price point of view, the best ones. Yeah, and if we, from a ZF point of view, have to request or choose magnets, it was because of the high competition on the market, in the most cases, the case that you buy cheap magnets in China. And there was some second choice to go to Asia, so especially Japan, where we have a few magnet suppliers, also with sometimes limited capacity, that are our standard ways. So I would say the last 15 years. But now, and that was really good, the last years, we saw as a tier 1 also some requirements in case of, okay, we want to buy magnets with a headquarter outside of China, or production outside of China, supply chain, or maybe magnets that are more sustainable, for example, defined with a product carbon footprint or with a recycling share. And that really open us as a tier one, because we are a little bit more like the mirror of the industry, the door to say, okay, then we can switch our perspective also to Europe, for example, with some magnet suppliers. But you know it, Europe is really in the beginning of this situation, because we have no mining, we have only limited capacity for separation, for metallization. So we go in some challenges, but we are really interested to support this situation. But we need this door openers. Yeah, yeah, and then we see NAFTA, or especially USA, investing a lot in mining, in separation, and year by year, the amount of magnet suppliers increasing in USA, and we see here a really strong dynamic. And if I could say it today, sometimes it looks like that it would be easier to import magnets now from USA to Europe than really establish a strong supply chain in Europe from the current point of view. Yeah, and like mentioned, we need this door openers, yeah. A real requirement to get or to source ex-China magnets, to source sustainable magnets. And if you want to source sustainable magnets, you also have to keep in mind how will you define some requirements? So what is currently a specific CO2 footprint of a magnet? Can you go to a Chinese mine and really check here the data, the condition of the magnet production, also the separation? So it makes it really tricky to get here at first a robust value. Yeah, and here it's clear, that's also the title. We have a very strong Chinese dominance in the field of magnet production. Yeah, that is challenging for us if we cannot go to China and get here really the traceability and the robustness and the stability of our supply chain. On the other side, and it only on the scale of a magnet production, yeah, we see also that the world is changing. We are not anymore the dominant OEMs in Europe that sell cars all over the world. We can see it here, for example, with this graph. So in 2021, the share of China in case of PHEV was about 30% or 45%, but it's increasing year by year. The largest market for e-drives and for battery electric vehicles in general is in China. Yeah? There's the party currently, and our OEMs in Europe are not joining, and that is also some problem, that we are currently not in the market with the high innovations, with the lowest prices, and with the possibility to really get here our own values in it, for example, in case of sustainability. That is also escalated by the situation that since a few years, we see this geopolitical fight between US and China, starting with 100% tariffs, and then now situation today is that 14 rare earth elements are now under export control. You get them, but you are not 100% sure if this will be also in future the case, and no one knows what will be with the next attack from the left or from the right. Yeah, and we, SZF, as a German company, it would be possible to say we sit here a little bit in between. Yeah, and see the topics, free trade. We want to recycle. We want to align on the Critical Raw Materials Act. We want to reduce CO2 emissions, and we want to also support the Green New Deal. But currently, it goes all, yeah, from the ranking, it's the secondary topic. The current most important thing is to compete in the market and to get magnets in general. Yeah, and so if we would illustrate a picture like this, what is currently for tier one the best strategy? So one way could be to say we avoid any heavy rare earths that are listed in the export restriction, for example, to go to HI free if possible. It's not for each design possible, but it is possible. Or should we go more in the direction to allow heavy rare earths because they have a really good technical impact? Yeah. Make a motor concept more robust, but buy them only outside of China in overseas mining facilities, for example. Is it currently in that situation the best way to make something like a directed buy to really build up a storage, also a strategic storage in Europe maybe, or in if we bundle all the tier one and the OEM demands, for example? Should we go to other magnet technologies that are not that dominated from China, like hot deformed or ferrites and so on? Or should we really go the way to say, okay, then if this is that complicated with magnets, then we avoid magnets on our e-drives, and then we have some drawbacks on the efficiency. That's a problem for the battery, but not for us as ZF. And so we offer only traction drives with ASM, SESM, and other designs without magnets. Or the last one, really try to build up something like a closed loop scenario where we know the resources that come to Europe stay in Europe and that they are used the next 1,000 years in the best case. Yeah, and it's a little bit a question to the audience. Yeah, which way you would choose currently if you are tier one, if you are OEM, or if you are a car buyer? Would you really pay some premium to be sure that the car that you buy not using any heavy rare earths from Myanmar, or that the magnets are more sustainable, for example, or that you support the European industry? So that's open question. Go to the next point, tailored material selection. So another lever. So going away from this strategic and really chaotic situation, for me as a material scientist, it's good. There are some material roadmaps for every magnet supplier. That's only an example. So you can see here a roadmap that shows the correlation between a coercivity, so the energy to withstand a counterfield in the e-motor, the remanence that is, for example, useful for torque in the e-machine, and the combination energy product. And the colorful illustration gives you some idea how many heavy rare earths do you need for which magnet class. Yeah, in the beginning, so for 10 years, for example, the first transmission systems use magnets with really high heavy rare earth contents on the range of 5 to 6%. With our generations a few years ago, pure e-axles, we reduced this value to about 2%. And currently we are in a situation where we say, okay, we can go to HRI-free magnets, or we can accept a little bit heavy rare earths, to get here a little bit more safety or to make the design more easier in case of cooling. But that is the current situation. So we can, over the years, because of innovations and because of reduced technical requirements, reduce our amount that we need for heavy rare earths in general, and also the magnet weight is reduced. And that is illustrated in this picture. So if you would open a HyPride system that was starting in SOP 5-6 years ago, then you will find about 1.1 kilogram magnet weight, and about 300 grams neodymium and 50 grams heavy rare earths. For standard e-drive, 800 gram and 60. Yeah, and if you open a sports car with a more performant e-drive, then you can have the situation that you will find 4.4 kilograms of magnets and more than a kilogram of rare earths. Yeah, and this calculated with yearly demand of about 100 electric traction drives, always using our ZF motor in the best case. Yeah, you see easily, we would need thousands of tons of neodymium and heavy rare earths. And it's not acceptable under the premises that currently we get a lot of rare earths because of illegal mining. And we have limited resources. So it's our responsibility as a tier one and as industry, as a OEM, to reduce this amount year by year. And in the best case, avoid the heavy rare earths. And then in the next step, also substitute the light rare earths if possible, or go to other magnet alternatives. And to get now the link to the sustainability, it's clear that all these elements have a specific CO2 footprint. And if you have higher amount of terbium and dysprosium that is limited and where you have more complex separation processes, you have also the situation that you have a higher CO2 footprint. So it's a good way to reduce the heavy rare earths to get here some good starting point, and then decreasing the sustainability, the CO2 footprint step by step with additional topics like better separation processes or more electricity in the production and renewables and such things. Yeah. But that is the link between selection of a magnet and also the case CO2 footprint. Yeah, and in the case of a hybrid system, we were more in this range here, so 3 to 5 to 6%, and have you really a high additional add-on on the CO2 footprint. Another technology that is really most common, so since decades, we use so-called GBD process. So the heavy rare earths are not homogeneous in the volume of the magnet. They were diffused from the outer geometry, so from the surface. And so you have something like a gradient. Yeah, and this gradient is really good because of our counter field from the traction drive. We have also the situation that we need the heavy rare earths only in that positions where we have high counter fields and where the magnets have to withstand these counter fields. And so one solution is, it's in that example, only use the diffusion process at that small area where we have the high counter fields. So it's called localized GBD, not covering the full magnet surface with heavy rare earths, but only really small areas where we know in that special positions, volumes, we need the higher requirements. And so we have also possibility to reduce our composition, our need of heavy rare earths, and also improve the CO2 footprint. Then I come to the last point, advanced technologies. And here I want to give you first some basic examples. So the same examples like in the slide before. So if you have a hybrid, it's often the case that you have here a lot of mechanical components, and the rotor with the magnets is more like a filigrane ring toroidal structure. Yeah, and so you have not enough space to make some fancy things with the magnets, or cooling is also sometimes challenging because you use the oil from the transmission. And so here are a little bit limited, but in case of e-drives, it's really fantastic that because of the amount of layers, of the angle, of the size, of the magnet weight, you can tailor a lot. And you can, for example, only use in the first positions with the highest counter fields in the e-drive heavy rare earths, but in the next layer, you reduce it and reach, for example, HI-free magnets already. So you have sometimes in one rotor concept 3 or 4 different magnet grades that you can combine. And something that is really significant change the last years, the cooling concepts. So in the past, it was a normal thing that you cool in the shaft from the rotor, but today, outer diameter of the stator is cooled. You cool directly on the copper windings because they produce heat. You can cool on the magnets because they produce also heat because of eddy currents that occur. And so you have many additional levers now to reduce the requirements. And that's the reason why we are also currently in our new base kit designs can use HI-free magnets and reach this step now to get here really also more flexibility in case of export restrictions if everything stays on the status that we have today. And also to say, yeah, a magnet is not only a block. So I already mentioned the GBD process, but you can also use segmentation. So make the magnet volume smaller. Because of this, you have a lower amount of eddy current losses, so AC losses. You can make it axial, tangential, radial, and then you have also sometimes really fancy situations that a diffusion process goes in axial direction like this, or in tangential direction like this. So it looks like a simple block, but you can make a lot with such a magnet. And the last one is that also the situation, how the magnet contact the rotor, for example, is the magnet epoxy coated, then you have an isolation coating and you not produce additional losses. But if you use a passivation, it's also really important, is the magnet glued on one side? Do you have some connections with mechanical components? Because this produce also global eddy current losses. And so you have here also the combination of more system relevant aspects, the magnet properties, the coating, the fixation concept. So it's really a fantastic thing what we can make, or what all of us can make with magnets. There's a lot of potential also in future to lower our requirements with this better understanding of this system related behavior. And that would be my summary. So I give you some insights in the topic strategic supply chain, tailoring the material selection, and this examples of advanced technologies. And we, from our point of view, would say we have really the potential, the lever to reduce our CO2 footprint of our e-machines in a significant way. It's only the question to have here really the reason, the requirements to do so. And here sometimes it looks like that every day the strategy from Europe, from China, and from US are changing. It's really hard to say what will be the future, and we as a tier one can only be as flexible as possible. But I want to show this last slide. It's only more like a conceptual one. So it was my trying to illustrate a very subjective view on the topic global situation on magnets. Yeah, and I tried to highlight some topics. So what is my thinking? And I structured it in four levels. The first one is the car buyer. So to really make something like education that everyone is sure that electromobility is our future, and because of climate change or because of values that we have as European, that we have really also this promotion again, because we see that it's more complicated to buy some unknown. And battery electric vehicles is really a special thing. If we compare it also with our smartphones that are every 3 years damaged because of the battery or something else. And then really this commitment that we are pushing the topic made in Europe and not accepting that we source in future everything from China. And so I tried to highlight some of the aspects, but I'm now not sure. Nabil, I'm over the time, or it's only for discussion.
Thanks. So we can wind up now. And thanks, David. And very exciting and eye-opening presentation. You touched technology, you touched market, geopolitics. Fantastic. So we will reserve. We have a couple of questions. We will reserve it towards the end because it's already, we have 2 more presentations in waiting. But maybe one question, because a couple of times you said, it was eye-opening for me that 37% of the all motors PCF come from the magnet. And then did you do a full value chain? Where is the most impact come from in the magnet making? Only the magnet making, or are you also looking at the raw material processing and sourcing and metal making, etc.?
Yeah, we tried a lot. So on one hand, we tried to get the primary data from our, for example, Chinese magnet suppliers. But here we see really a large variety of different response. And sometimes a magnet, a CO2 footprint for a magnet is in the range of 2 to 4, because they're argumenting that they use 100% pre-consumer scrap, for example. And then you have, on the other hand, a maximum that is 100 or 120, because of the fact that they really make the deep dive in mining and separation. And from my point of view, the separation step is the largest lever, and the scope 3 in general. And we understand from a point of view of a magnet supplier, if they use 100% renewable energies, collect the cutting waste, and also try to reuse the gases, then a magnet production is, from a sustainability point of view, really a good process. It's only the steps before are critical. Yeah, and
Yeah.
how to calculate if the mountain in Myanmar is destroyed and the population is affected by this chemicals.
Yes.
Yeah.
Yeah. Thanks for that. And we will keep the rest of the questions towards the end. I also encourage the participants, to put your question in the Q&A box, and we will read it towards the end. Thanks again, David. And we'll give you some questions at the end. Now we have the next presenter from VDA, the German Automotive Association, Karol Bednarek, who coordinates the working group on raw material availability at the VDA. Since 2017, this working group has established raw materials monitoring, focusing on battery raw materials, rare earths, and sustainability. The working group of the VDA provides its members with pre-competitive market information and forecast up to 2035. So, Karol, thanks for joining us, and the floor is yours.
Yeah, thank you, Nabil, and thank you for having me and giving me this opportunity to present here at this nice webinar. Before I start about the topic and about the applications in the automotive industry of permanent magnets, let me please briefly introduce you to the VDA itself. So the German Association of the Automotive Industry is pretty old. Next year we will celebrate our 125th anniversary. And what makes us very special in comparison to other associations is that we combine the OEMs as well as the suppliers under one roof. So that's why we have more than 600 companies in our association, representing a primary workforce for about 730,000 people in Germany. And as I mentioned earlier, we do have 3 manufacturer groups. The suppliers are the biggest group that you can see here. Nearly 500 members are at the VDA and at the supplier side, 21 OEMs, and we have 63 companies producing trailers, bodies, and buses. So we do think that thanks to this organization, we do have a pretty good feeling about automotive supply chains because we know the perspective of the OEMs and we know the perspective of the suppliers. And of course, the interests of both these groups are completely different in some cases. So we also get a lot of insights in this negotiation processes. From this perspective, of course, there will be no surprises to what David already said. So please, just a little bit expectation management here from my side. I will a little bit focus a little bit more maybe about policy making and other stuff. You've seen this overview maybe, and David already showed us the same slide, let's say, in a different representation. But there's, of course, more than just one permanent magnet that can be used in the automotive applications. However, they differ a lot when it comes to their maximum energy products, and therefore also about the amount of space that that is needed for them. So, as David already mentioned, when you have a neodymium iron boron magnet, of course, the energy product is the best. Therefore, you don't need much of it to have the same strength as a ferrite magnet, for example. So if you want to switch from an NdFeB magnet, for example, to an Alnico magnet, then you also have to calculate more space. And the question is, do you have the space in the automotive application that you're looking for? And therefore, of course, you have different aspects that you have to consider when purchasing those permanent magnets. So first of all, do you really need the strength in such a small space? And therefore, size, shape, and weight really makes a strong case for certain magnets. Then temperature resistance, which also David already mentioned, really defines also the content of heavy rare earth elements, shock and vibration resistance, durability, especially, for example, corrosion. If you are looking for an application for a neodymium iron boron magnet, then of course corrosion is a thing. There are layers around it. You have to make sure that corrosion is not destroying your magnets. So therefore, we think that, for example, samarium cobalt magnets will have a better case, for example, in offshore applications for wind turbines, because there is a lot of wind and a lot of water that maybe can lead to some corrosion. And the FeB magnets maybe are not the best solution there. And then, as David really made a big point out of it, are the ESG requirements, green magnets. You also have to consider it. And last but not least, of course, the price. And as you can see in the slide, there is no such a thing like a magnet that is really perfect for every job. So you really have to consider what are your targets and what does really your application need. And when it comes to the car, you might think already know it. There's not only the drivetrain in an electric vehicle, but there are a lot of different other applications which are electrified. And therefore, when you have a small electric motor in it, you probably also need a magnet for this application. So we tried to just point out finger to some applications in our automotive in our product, which is the car. And I can tell you the list really goes on and on. So it's not finished here. That's why we called it etc. But maybe some people don't know that you also need those magnets in your normal petrol engine car. So if you have windshield wipers or airbags or let's say window power windows, electric side mirrors, in this all applications there is a small electric motor in it which requires a magnet, and probably you will have there also an ND-FEB magnet in it because you don't have that much space when it comes to the doors, for example, in the mirrors, or also in your windshield wipers. So that's why the weapon of choice here actually is really the ND-FEB magnet. And I'm really happy that David had similar figures to the amount of certain permanent magnets per application. You can see that we calculate around 500 grams in a normal internal combustion engine car. And in the PHEV, you have, of course, a little bit more in the BEV per se as well. But you also have a lot of magnets in mild hybrids that are then hidden in the transmission or in the gearbox, as you can imagine. Here, we just wanted to show you a little bit about, or inform you about how those ND-FEB magnets are built. So there is varieties, and I think the slide David showed with different attributions, of course, really, let's say the function forms the form. So if you are in an environment where temperature is rising above 150 Celsius, then of course you need heavy rare earth elements. And those are, of course, right now a little bit of a problem maker because of the Chinese export restrictions, which went into force in April this year. But you can see the content of those heavy rare earths really can vary a lot. In some cases, we also have zero. Unfortunately, in this source that we used, this case wasn't pictured. But in some cases, you also have ND-FEB magnets free of any heavy rare earth elements. However, when it comes to the Chinese export restrictions, you have to go to a laboratory and prove that they're really free of heavy rare earth elements. And if they have just, a little bit of powder on them, let's say, which is nearly nothing, it still accounts as content, and therefore you will need to have a export license to export these magnets, which of course leads to a lot of documentation and a lot of we can say problems, because to apply for an export license, it really takes time just to get all the documents together, especially the documents that you need for the end-use certification. So if you are a Chinese exporter or producer of magnets and would like to export those magnets to a supplier in Germany, then of course you need this document. So the originals of the supply contracts, documents for the exported products, end-use certificates. And now I should add an S to this slide, because actually right now it seems that everyone who will be using products which contain this magnet, which will be exported with this export license, need to sign this end-use certificate. So there's more than just one end-use certificate, which of course leads to a lot of time for the importer actually to talk to all of his clients and ask him to sign this end-use certificate. Therefore, we think that you need approximately 1 to 2 weeks or 3 weeks even just to get all the documentations ready to apply for an export license. Then in the first check in your local administrative office, which hopefully just takes 10 days, they will just approve or checking up whether the application is complete. And after that, it will be sent to the MOFCOM, and there it can even take up to 60 days. And this days is working days this time. 60 working days to approve your export license or not. However, we heard in some cases it even took longer than just 60 days. So you can imagine there's a huge delay in this supply chain, which also can lead then to export disruptions, at least, or to production disruptions, or maybe in some cases even to production stops, which so far as of now haven't happened that much at the automotive industry. However, we heard from other industries that they are waiting for 6 months now to get a license, and of course within this time they couldn't produce anything. And now I haven't prepared a slide for the new export restrictions that were published on October 9th, 2 weeks ago. But of course, there are new export restrictions for new heavy rare earth elements. We are still trying to figure out how much we are affected by these export restrictions of these 5 new elements. However, we are of course affected by export restrictions regarding the knowledge and using the technology and everything, which will be enforced even extraterritorial. So even outside of China, when you're producing magnets which are defined in the Annex 1 of the Announcement 61, then you also need to apply for an export license if you want to re-export those materials or these magnets. This, of course, will lead to another bureaucratic burden, which we, of course, also have to face, which will lead to additional challenges. And because they are extraterritorial, we think that there will be a huge wave of applications, and we just can hope that the MOFCOM will prepare, or will build up some workforce so that really the amount of those new applications can really be handled by the MOFCOM, actually, in a timely manner. So the question really is, what can you do to reduce the dependency? Because right now, when we look just into Germany, I'm not talking now about the German automotive industry, but Germany as a country per se, 94% of those NdFeB magnets are coming from China. And also when we're looking into the rare earth elements, which are in those magnets, we see that especially for heavy rare earths, we have a dependency of over 100%, and on those light rare earth elements, 85%. So we can imagine that those new export restrictions, for example, if you want to build up a new value chain for permanent magnet production in Europe, we probably will facing also those export restrictions because we will probably be using Chinese material to produce them. So what can you do? Of course, you can still try to diversify, which is very, very hard. David already mentioned some other countries who are producing magnets, but those capacities which are built in those other countries are not really built to expand and to provide also other countries. So they are producing for the domestic demand, and for ramping up in this field, this will be very, very hard for those countries. So therefore, also there, new value chains need to be built up, which also takes time. We talked about recycling a little bit. We probably think that the huge feedstock coming for recycling will be production scrap at the beginning, and therefore in Europe we don't have that much production of magnets. So the amount of production scrap in this case is also very limited. And the first big wave of electric vehicles which are being dismantled will be probably in the mid-30s, and then they will have maybe an impact. But when you remember my last slide where I showed you the amount of different magnets per car, it's not that easy to really get those magnets out and recycle them. So if you are looking just the ICE vehicle, where we don't have a traction motor, where maybe over 1 kilogram of those magnets is concentrated in a little area, where you can just tear out the traction motor, for example, and then start to figure out how to get those magnets out of this traction motor. And the other applications, it could be very, very hard, because in some cases, in the sensors for braking systems, for example, you don't have that much of magnet there. So just to get there takes time, just to dismantle this brake system. And in this case, where the magnets are very, very small, we probably don't see a good business case for the recyclers to make the effort to get those small permanent magnets also out of the car, and therefore leading a contribution for a feedstock of recycling. So we think that, of course, when you have loudspeakers, for example, in some cases you even have 70 grams of NdFeB magnets in one loudspeaker, then maybe it's still, because it's very easy to get to a loudspeaker, this would make sense. But to get the sensors out of the other applications, and also the airbag and the power windows, this is probably not a very economic case. So we don't think that this will lead to a contribution for recycling, to be honest. But still, I mean, we are very contributed to this idea of circular economy. The automotive industry already has a circular economy built with the internal combustion engine cars, and there's no difference when it comes to electric vehicles. So we will be building up those value circles, if you like to call it like that. And also then permanent magnets will be recycled from our cars, just to give us a little bit more certainties to get a feedstock of new permanent magnets coming out of Europe, possibly. And then substitution. I mean, of course, there are some compositions that don't need heavy rare earth elements. David already showed it to you. We already have this in place for traction motors as well. So if you're looking at ZF, also Schaeffler, they're producing traction motors that don't need those heavy rare earth elements, and they're already in the cars today. But when it comes to those sensors, pumps, and motors, this will be very, very difficult just to replace them with some other magnets, which are not neodymium iron boron magnets, because you have the space restrictions. You maybe not need heavy rare earth elements in them, but when it comes to braking systems, for example, you probably would like your brakes also to work when it's very, very hot and brakes are producing a lot of heat. So we don't think that they will be replaced by magnets without heavy rare earth elements. And you also cannot, it's not that easy to switch from a sensor with magnets to a light sensor, for example, because we have a lot of vibrations there, and this could lead to wrong information actually transmitted by this light sensor. So we don't see a big possibility to substitute there. I just prepared a small slide comparing the different traction motors, but I think David did a really good job there, just presenting the different motors. So I don't want to go much into detail here, but maybe what's also important to understand is that then PMSMs, these permanent magnet synchronous motors, are very effective at lower revolutions, but they are maybe not that effective at high revolutions. So we see a lot of developments combining those two engines, or even sometimes PMSMs with induction machines as well, just to have the advantages of both technologies in one car. So in some cases where you have a dual motor system in the car, you probably have two different traction motors there using different technologies. What about legislative making? So we just want to point out that when it comes to permanent magnets, it's very difficult right now, because we do have the Critical Raw Materials Act, which defines a lot of recycling targets or labeling issues, data carrier, how to calculate methods, recycling for content, for example, what recycling feedstock is allowed. So is it post-consumer waste or is it production waste? And then we have the end-of-life vehicles regulation, which will be now replacing the end-of-life vehicles directive. So it's still now in the trilogue, but in the documents that we have on our hands when it comes to the end-of-life vehicles regulation, which is our central legislative piece when it comes to circular economy in the automotive industry. So this is our rule book actually when it comes to circular economy. We do have different targets for actually everything. So when it comes to labeling, this CRMA states that you have to label all traction motors, whether they have or have not a magnet. And the ELV regulation, you just have to label if there's a magnet in it. The data carrier also looks a little bit different. The calculation methods on recycling content are not defined yet, but the timelines to get there are different in the ELV regulation and in the Critical Raw Materials Act. And recycling feedstock, I already mentioned it. And last but not least, as I mentioned a little bit earlier, the scope. So the Critical Raw Materials Act requires every product which is using permanent magnets that has more than 0.2 kilogram of magnet in the product, just to identify where the magnets are, how to dismantle them, what chemistry they actually are, and all this information has to be stored in the data carrier. The ELV regulation realized that maybe it's not that sensible to create such a big book of magnets that you probably will never get out because they're in the sensors. So they're focusing only on the traction motor, which of course, for our perspective, makes really sense because this is the amounts which probably will make a case for recycling as well. And the timelines also a little bit different. So just, last but not least, our key takeaways. I don't want to go too much into detail about this ones. And yeah, thank you for listening and looking forward for the discussion later.
Yeah, thanks, Karol. Very knowledgeable and an exciting presentation. Covered a lot of things. And I want to announce here, because you mentioned on the regulations from the European Commission side, we have a conference on rare earth and magnets next week in Stuttgart at Mercedes-Benz Museum. So I know that many of you joining this webinar have registered, but if you haven't got a chance to register, please do. And we have a dedicated workshop on the critical raw material, especially Article 29, that we want to get the input of the Article 29, which is basically recycled content in the product. So the also the CRM implementation phase. So this is act phase, then the implementation phase. How? So I like to invite all the participants if you can join us in Stuttgart next. So before I go to the next, maybe one question from my side for you, Karol. You mentioned, you also covered the export restrictions of the Chinese. And so you said only one license per purchasing order. How that is defined, how many tons, for example, you can include, or how many kilograms you can have in one license application, how it is defined on the Chinese side?
Yeah, so there are not no limits or per se limits from the Chinese side. Of course, they're comparing to the amounts of shipments from last year, and if you are trying to export more than you did last year, then you will face some problems. So they're really making a case. So if they think that you are maybe stockpiling some of these magnets, then they will make it hard for you to export them or to obtain this license. However, with purchasing orders, and if you have a export license which will be valid for 6 months, you can use this export license for a maximum amount of 12 shipments, and the sum of the exports cannot exceed more than 5% from the purchasing order, or from the purchasing order between the supplier, the exporter and the importer. But this 5% is more like an anecdotal knowledge, actually, because it is not defined anywhere in this legislative piece of work. However, they started, the Chinese Trade Ministry, MOFCOM, they started to do a consultation where they also introduced this 5% margins on those export volumes, but they are not actually into force right now. So we are still waiting when this regulation, which was under consultation 1 month ago, will actually be the new rule.
Yeah. Okay. So we see how it evolves. Because a lot of disruption for the EU and Western automotive supply chains. Thanks again. And we have a couple of more questions that I will keep for towards the end. So now we have our last presentation from Misha. He is from IFPEN. And he's also, IFPEN is a partner of the consortium member of the Magellan project. So Misha earned his master's degree in mechanical engineering from SUPMECA Paris, and specialized in energy and powertrains at IFP School. After working at Renault in France and Istituto Motori in Naples, he joined his current company IFP Energies Noelle in 2012. Over the years, he has held various roles, including engine simulation engineer, powertrain systems engineer, and system architect. Well aligned with our webinar topic. Currently, as a project manager, he leads the developments of electric propulsion and component systems. Misha, I like to welcome you and thanks for joining us. The floor is yours.
Thank you very much, Nabil. Thank you as well to Carol and David for their presentation. I really appreciate it. I don't know, do you see my screen and hear me well?
Yes.
Okay, great. So I'm very happy about the last two presentations because it introduces quite well the mine without too much overlapping. So yeah, as we see, this rare earth problem is now global and very big, vast. As such, the situation requires that each entity make its own, even small contribution, to find a way through the problem. My presentation will focus on the contribution of a motor designer. So it's a motor designer point of view to complement the other two presentations. So just to make to do it like others, a few words about IFP Energies Nouvelles, but really in order you can understand our point of view on this subject. Then I will be setting a common understanding about what is the problem, and finally we are going technical about opportunities, a practical case, and the solutions we will have in this problem. So at a glance, IFP Energies Nouvelles is a public research institution, a training center, and an industrial group. We are situated in France, though we have an international coverage and scope in the field of energy, environment, and mobility where I belong. So our purpose is to, as a public institute, is to help startups, small and medium companies to bring the innovation on the market through different actions, and as well technical as financial or patents, etc., in order to boost the competitivity, industrial competitivity, of course, and employment around us. So the position of IFPEN is in between the research with low TRL or components or material providers, and on the other side, the market, high TRL market propulsion system providers. So the boundaries are not so, let's say, vertical, because we are collaborating and having partnerships at those interfaces. So in few words, at IFPEN, we are developing and validating electric motors, power electronics, and software, mainly up to TRL7. So about the rare earth challenges. On this picture, you can see a global rare earth production and reserves. Of course, it is from 2019, though it's still true. The first thing we can see here is that rare earths are not rare at all. Still, secondly, we don't have them. We don't have any of them in Europe, at least not as much as we would like to. And third, there is a high concentration of resources, a tremendous level of know-how about processing and production in China, like David mentioned it, with low or no competition. If we look through the chain, more we get close to the produced magnet, lower is competition. So we are in the situation of the monopoly on this production side. So on the other hand, we have our automotive industry. So from the automotive side, before 2010, I think David's first slides were very speaking. Before 2010, on the automotive market, we had mainly in gray color induction motors leading the market. And then we had DC motors in blue and permanent magnet assisted motors in yellow. After 2010, we can see that the permanent magnet assisted neodymium iron bore base magnets skyrocketed up to 85% of the market, with only induction and wound rotor as an alternative solutions, led at this point by Renault at first, then BMW, and then everybody else. And David mentioned this. And as a motor designer, I can understand fully the trend, because with magnets, permanent magnets at least, we can find a way to satisfy, okay, I'm simplifying, but we can find a way to satisfy more or less any requirement in efficiency, volume, whatsoever, really. Though, since April, with magnet exportation controls and licenses, and I thank Carol for the complementary information, the question is, what are our alternatives? So my point of view goes towards diversification, the same as Carol said. Diversification mainly of technologies, of motor technologies, together with permanent magnet circularity. I think both are very important. And the remaining question is, how much diversification are we capable of? I think this is the question today. So about mitigation approach, let's say I can speak better about those I implemented 7 years ago at FPN, and I believe in. And they are quite similar to what we heard earlier, but let's start. So we have 3 pillars of each historically. The first one is the rare earth reduction through, okay, topology choices, as for instance, permanent magnet assisted synchronous reluctance topology, which doesn't rely too much on magnet performance. Heavy use of computer-assisted optimization and reducing magnet stress in the motor finally, mainly on the thermal side, which has impact on heavy rare earths need like terbium or dysprosium. The second pillar is about competitive, and I insist competitive, alternatives based on rare earth magnet substitutions or substitutes, like for instance ferrites. Just to mention the ferrites, even if the magnet is poor, we will see at the end of the presentation how we can make it competitive today in the automotive industry. Or even we can imagine other alternatives, magnets having lower performances. And this is what I'm speaking about today. And going up to completely avoiding permanent magnets, as it is the case of the pure synchronous reluctance motor. I will not be speaking about this one in this presentation. And we can imagine as well wound rotor and induction motors, which are already on the market and very good alternatives for higher segments. The third pillar is all about designing the powertrain from scratch for lifespan extension and easy and automated end-of-life magnet collection. And the rare earth circularity motor designer contribution, at least, is all about preparing the future with magnet collection enabling and using recycled rare earths with caution. So to have a leverage to manufacture more motors in the future with the available quantities of the rare earths we have today. So from technological point of view, how to reduce the dependence of the rotors on neodymium-based magnets. So to illustrate that, I have a chart which shows permanent magnet synchronous torque, the left-hand side, versus reluctant torque. Reluctant torque is the one produced only by the electrical steel flux barriers without magnets. So the indicator I'm following here is the kilowatts of mechanical power produced per kilogram of magnet. Of course, on the left-hand side, upper left-hand side, we will have all the surface-mounted permanent magnets, axial flux machines, etc., relying heavily on the permanent magnet performance. Then, if we look to the second rotor, which is a little bit buried in the rotor, magnets are buried in the rotor, we can see that we produce 45 kilowatts per kilogram of magnet. Going still forward, when we see that adding a bit of geometries in the rotor can almost double the performance in terms of kilowatts per kilogram of magnet, and then going to the even higher investment in terms of geometry optimization with here 2 flux barriers, we can reach 100 kilowatts per kilogram of magnet. Basically, we are producing two motors with the same quantity of the magnets with this PMR Synrel motor in comparison with the previous 2004 version. On the other hand, of course, we have pure Synrel, which doesn't have any magnets, as well as wound rotor or induction motor, which are great alternatives. And we have here a technology I will be speaking about, which is very close to the pure Synrel and not relying so much on on the magnets. So we can see that investing in the rotor flux barrier geometries and their optimization reduces dependence of the torque on permanent magnets. So there is something to be looked at on this side, because with this approach, let's say this approach opens the gate for reducing the neodymium magnet quantities per motor and providing a leverage when it comes to using recycled rare earth material and producing more motors out of them. And the second, it opens the gates to implement substitute magnets having lower performances. And I think this is another interesting point. So a practical case. I'm showing you a rotor, and it's not a promotion for FPN solution. It's just one of the possible solutions to answer the question. And I hope, I know that other tier ones, probably ZF and others, work on these problems, and I'm very happy about this, just to speak about and make general knowledge about this approach. Not only IFPN solution as such. So going back to the presentation, in 2020, we have tested this approach by pushing the rotor reluctance at the maximum and extending the approach towards end-of-life collection enabling. So to do so, we have gathered the feedbacks about current technological obstacles from end-of-life collecting and recycling sector. So we could set the development requirements from beginning, considering those problems. The rotor you see is the very first result of high reluctance rotor, taking advantage from, in this case, 2020, fresh material, non-rectangular powder injection molding magnet by CLD10. The motor produced 270 Newton meters, 190 kilowatts, running up to 80,000 RPM. And most of all, it reached 130 kilowatts per kilogram of magnet, which was 25% improvement in comparison with the state of the art at that point. Later, we saw a motor closing the gap with 110 kilowatts per kilogram, but this was in 2023, I believe. This performance was achieved through the rotor flux barrier multiphysical optimization on one hand, and small geometry implementation. I will show you here in the electrical steel and magnets. So we could reduce, or I think even avoid gluing those magnets. As you can see them here, they are not glue, there is no resins around, which allowed us, after the testing the motor, to extract the magnets without even demagnetizing them in ovens. So I think this is an interesting aspect. Is it industrial? Not at this stage. Is this something to work on? I think, yeah. I think, yes, it is. So this is our starting point. I wanted to show you. And so now the next step about technology maturation, along with high performance magnet pilot line development in Magellan project, is the next slide, if you want to go on. Okay, great. So if you're here, I think you already know something about the Magellan, so I'll be short. So Magellan project is about developing the process and the know-how about high performance magnet production, incorporating recycling rare earth material, about 25%. And as well developing a surrounding ecosystem, which is necessary, absolutely necessary, if you want a European ecosystem to be run. When we look to the flow chart on the right-hand side, I don't know if you see my mouse, we can see that even though the motor design is not of first interest when you're speaking about magnet process production, but the motor design is an enabler and has impact on almost 50% of the activity, which contributes to reach the project goals. And that is why powertrain design should update their development functional requirements so it can positively and with limited cost contribute to the magnet circularity in Europe. So in Magellan project, our reference for the process, our reference for developing and qualifying the magnets is the high-end motor from a premium vehicle, which is Maserati Folgore. So we are targeting the magnets and motor performances of this vehicle. And in this way, we avoid any under or over quality development on the magnets very early in the project, limiting investment, which is natively very heavy to develop a complete process. So Magellan magnet batches are evaluated in a digital twin in a short closed loop, and then experimentally at the component level, hystereograph, for instance, and finally on a full power electric motor in testing bench FPN, of course. So about digital twin, I will not extend on this one, but it's a digital electromagnetic multiphysical digital twin we use in-house. So based on a mathematical layer, dealing with optimizations, and we have a multiphysical simulation, which are on the second layer. In order to set up this simulator, we use bibliography, data about the reference motor. We use measurements, characterizations, and we targeted two user-oriented approach for our magnets. So the first one is very natural, which is early adopter point of view, which is direct shift. By the same geometry we change the material. We go from Chinese magnets to European magnets, keeping the performances and geometries. The second aspect, the second approach is optimizing the rotor on purpose in order to reduce the quantity of the magnet for the same performances, and in such a way produce a leverage for use of recycled material. So at this stage, what was done in the simulation is the rotor wasn't optimized. We just took the rotor, the geometry of the rotor you have seen initially, and then we rescaled it, just keeping in mind that the mechanical aspects were validated, but no electromagnetic optimization. And it was done to put under control the target of at least 20% reduction in permanent magnet mass for the same performances. So on this slide, you can see the magnets performances. In blue line, you can see the reference motor magnets. And then in orange, the Magellan recycled magnets. And then we have in green, the PIM magnet. What we can see here on this graph is the induced voltage of the motor at 80,000 RPM. And what you can see is that the back EMF is almost very close between recycled magnet and reference magnet. Recycled magnet is a bit lower because it's very first batch and it has still some improvements to be done, namely in coercivity and as well in the remnants. So this is why we have a smaller performance in back EMF. And on the other side, we have a PIM rotor, which has 20% less magnet and produces less back EMF, which is quite handy for power electronics, to be honest. But we can expect that our non-optimized PIM rotor is underperforming. So what we can see here on the torque versus speed curve is that our PIM rotor, non-optimized geometry, produces more torque than the reference motor with 20% of magnets less and lower performance magnet. So it's quite interesting as a result to start with. The second aspect is in the power band here. You see that we are quite close to the reference in terms of power, but we are lacking a couple of kilowatts. And this will be a job of optimization of the rotor geometry and the reluctant torque in order to close the gap with the reference. When we do direct, of course, when you do the direct retrofit by the recycled magnet, what we can see is that we are very close today. And I think with the second, third, and fourth batch of recycled magnet from Magellan project, we'll really close the gap and the target of being able to produce a high performance permanent magnet in Europe with recycled content will be possible. So final, some key takeaways from my side about the initial question. The first one is that high performance European permanent magnet production with recycled content is necessary. It's necessary for the health of our industry, not only automotive industry, like we saw in the Carol's presentation. And I'm really important. I think the motor designers, actors have a very important role to play, not only in short term, but in long term, because they are enablers of circularity for the permanent magnets, really. And they have to work with European permanent magnet production companies, which are setting up now. And finally, this approach we are putting in Europe about production of permanent magnets has to stay environmentally healthy in order to avoid solving one problem, and by solving this one problem, falling into another. So I will finish on this one. Thank you very much.
Thanks, Misha. Again, another very interesting presentation. A bit more detailed on the design and drive motors. Thanks again for joining. So we have almost 10 minutes left, more than 5 minutes left for the Q&A, and we have a few questions received in the chat box. And yeah, so maybe I'll start with Misha. There's so you explained well on the motor structures. Initially, you also said compared with other motors like wound rotor and also induction motors, and you mentioned OEMs like Renault and BMW using a different kind. But all three presentations said PMSM, permanent magnet motor, is the most efficient. Now, how the alternative motors fit there, and how, for example, the other OEMs match that same efficiency? Is it through battery, or there is other mechanism that could match the performance of the permanent magnet? So, yeah.
I think that, of course, the answer depends on the segment. The high-end CD segments of the vehicles require very high efficiency and very high power all together in a limited space. So for those C and D bigger vehicle segments, I think wound rotor is a good alternative in terms of efficiency and power capability, though the challenge is very difficult. This is very difficult. And on the other side, for B and C segments, I think other alternatives like ferrite motors, which when designed properly, because ferrites are quite capricious, when designed properly, can match the efficiency of the permanent magnets. But they cannot be as versatile as permanent magnets today. So I think it depends really on the application we are targeting.
Yeah.
By design,
thanks,
let's say, by design.
Yeah, thanks for that excellent answer. So again, on the efficiency, and so we also see the historic development of even the permanent magnet motors. For example, you showed in the Prius, the kilograms of rare earths, but also heavy rare earths that could be reduced. So David, question to you: how from the motor manufacturer perspective, how you foresee maybe at 2030 or beyond perspective the requirement of the heavy rare earths in the motors? Will it still would be required, or you think that we could phase out the requirement of the heavy rare earths because of the developments in magnet material, but also overall efficiency development in the motor designing? Yeah.
Thanks a lot for this question. Yeah, if I see really this push after the export control in China, accelerating the development speed also at ZF side, I would assume that in 2030 we will not have the problem with the heavy rare earths anymore, but we have still the problems that we need the light rare earths and order this large amounts, and so that point of view I see not that critical. But in some applications, like I think mentioned from Carol, we will not have other solutions. And this magnet type is really fantastic because it's really strong, it's cheap in the production. We can recycle it in a really high efficiency. And I would say it's not the best idea to run with 100% in the other direction. Only because of this dominance, we need to find a good balance in between.
Yeah. So that's a good answer. And maybe next to the Carol, heavy rare earths is an issue at least till 2030, 35, and most of it is coming from or source from countries like Myanmar. It's end up in China, 100% end up in China. Chinese processing companies then feed into the magnet manufacturers, and we source it, and we don't have a law or mechanism to prevent it. But VDA associations like VDA with a large network of the users can prevent this. Is there any steps that, because you mentioned sustainability as the one key aspect that you're looking at or you're leading it? So is there a way that how you prevent that, or is there a way that you're working with the Chinese suppliers to prevent the raw material coming from countries like conflict countries?
Yeah, so I mean, when it comes especially to Myanmar, of course, we have a huge issue there. We also think that all of the material ends up in China, and it makes up of more than 40% of all the heavy rare earth elements on the market. And we are, of course, asking, or our members are asking their suppliers whether they can rule out that they are not using those heavy rare earth elements. However, because there's a law that they are not allowed to have any trade with Myanmar, they always claim that, of course, they are free of Myanmar heavy rare earth elements because they're not allowed to have trade with them. So there's a lack of transparency, 100%. We did try to make a little bit more transparency available through projects together with the GIZ, but also with the BGR, which is the German Geological Service. However, this process was very, very long, and at one point there was also no funding anymore from the German government for this project after 5 or 6 years. So in the last few months, we saw some movements from the Chinese CCC to make a difference, and they also started to do some webinars for Chinese magnet producers as well, just to show that probably they are having those heavy earth elements in their supply chain, and therefore this is not very sustainable. So we see this development, and when it comes to the content of heavy earth elements, most of our members think if they cannot rule out those conflict minerals, let's call it that, like them, from Myanmar, then maybe it's best not to use them at all, where you can rule it out. So that's why there are these developments, and of course, especially now with the export restrictions, even more drive came to those developments to not use heavy earth elements. But even before that, we've been looking into some forecasts for the heavy earth market, and we found out when it comes to the amount of heavy rare earth elements available on the market, by 2030, 2035, you will be not able to have a bigger content than 2% in those magnets because there will be not sufficient heavy rare earth elements on the market available. So this was also a driver for our R&D departments to reduce this content there. And yeah, I mean, this is everything we can do. We help our industry as well if they have some new initiatives to get more sustainable, more transparency actually, because that's where it lacks. Then we are helping our members 100%. However, we also understand that it's very hard in certain countries to get this transparency.
Yeah. So yeah, I understand the tough, working environment with the Asian players. So this also make a case for us, including the EIT raw materials, to help and develop alternate supply chain, and even in Europe. And David, from your the magnet requirement perspective, if you can give a figure of what could be your annual consumption, plus how you see alternate magnet projects coming in Europe, for example, and also one scenario is that maybe many of them will be in US, then we can source from US, but in cost comparison they will be higher. So how you foresee the magnet development in non-Asian countries? and your actual demand from
Yeah,
ZF perspective.
yeah, I cannot
Yeah.
say our actual demand, yeah, but I would
Yeah.
say if all the tier ones and OEMs in Europe would source in Europe or in NAFTA, then we would have a large problem because we have not enough capacity. Yeah, and so we have not the chance to skip all. Yeah, and my problem often as a tier one is if we are driven in this high competition that we have currently, and we are compared with Chinese prices, and they use Chinese magnets and Chinese raw materials in general. And so we have on our eDrive currently a that high cost pressure. We cannot use other magnets if we not have really the requirement coming from OEM side or from government side. And so this circle is running faster and faster. Yeah, and currently we see China has also problems with the domestic market, decreasing price step by step and for all raw materials, yeah. And no one knows where's the bottom line, and that is really the chaotic scenario. So I would say if now everyone would push it in Europe, we have not enough capacity, and it's also not in our mind currently. Yeah, we have other problems. It's not sustainability that is important; it's only to survive.
Yeah. Yeah, thanks for that. I think we are well on time. You know, it's we passed time. Maybe a final comment from Misha. So Misha, how you see the development, motor development, design development from the Magellan perspective? How is the solution? Is it when we could have that alternative magnet supply chain, or how positive you are?
With regards to what we are doing in Magellan, I'm very positive because in my presentation we saw I told you that we have a tremendous know-how in China. We don't have in Europe. I think we have to be honest with ourselves. And Magellan, but as well other initiatives, gives us confidence because we are getting there. Brown boundary diffusion, high performance magnets, and this know-how and equipment which is necessary when we can get it because it's only produced in China and now it's in Europe. It gives me confidence. I think we will get there, though, like Carol told us, and as well David, if there is no help from car manufacturers to require to input some recyclability or reuse of recycled materials, or even from Europe, encouraging all the ecosystem to do, even if it's not economically efficient, I think we could survive. This is one point. And the other point is really diversifying our technologies in order to use the permanent magnet only when it's really necessary.
Yeah, good point. And I think I should wind up with this. I would like to thank all our speakers, very excellent presentations, and also, the participant, who spent 1.5 hours here and providing their feedback through questions. But I also thank my colleague, I think Abuzar, I think he's online, and for organizing this system, coordinating with the speakers. Thanks, Abuzar. And also my EITN and Magellan colleagues who helped us in communication and setting up the webinar tool. And thank you all again. And I hope to see some of you at least in Stuttgart next week, where we will discuss almost same topic but more intensively on technology and market perspective. So thank you all. See you next time.